So reproductive rate, no surprise, how many babies at a time, that makes a difference. How soon you start making babies, what's the age for reproductive maturity, overall fecundity, what's the potential maximum number of offspring that you can have for a given population. Evolutionary fitness relates to the ability to reproduce and have those offspring survive, contributing to the next generation. There are quite a range of strategies, but we'll kind of look at two extreme ends, R-selected versus K-selected patterns. R is related to the reproductive rate and the growth rate. So these are things that can reproduce very fast when the opportunity is there. A lot of those young might not survive, but they can crank them out real fast when the opportunity occurs. These tend to be relatively small. They tend to mature quickly, not live so long, have lots of babies at a time, not taking a whole lot of care of them. This tends to be the there's an opportunity and seize it real fast. So situations that are less predictable or only exist for a short period of time, and there's not as much potential for long-term survival. For example, there are a variety of frogs and toads that will lay their eggs in temporary ponds and puddles. Okay, if they grow fast there, there's not much competition, not too much else living there, so they can gobble up all the algae. They're not competing with many other animals there. But those places dry up. There's only a short amount of time. So having lots of babies grow real fast and then come out of the water as little toads or frogs and then growing more once they're out is a common strategy under those situations. A lot of insects. Yeah, they're typically pretty small, can grow quite quickly, population grow fast, but it might crash fast too. A lot of weeds. Pop up, will grow, make seeds, die, and then maybe the seeds are successful, maybe not. But it's made a lot of them, chances of some of them succeeding, decent. K, on the other hand, are much more stable. They tend to have populations that stay near the carrying capacity, which we saw was typically abbreviated K. And so these have few offspring at a time, tend to be larger, longer lived, take a while to reach maturity and start reproducing. And this will tend to work in places where you have a fairly stable condition. So you can reasonably well count on the few young that you have to grow fairly well and survive. And with that care, there's a good chance that most, maybe all of those young will survive to adulthood as well. These are going to be good at what they do, tend to compete well against other organisms. The fast in and out tend to not be competitors so much in direct competition. They're jumping in on an opportunity that others aren't using, and so avoid the competition that way. So a number of larger predators tend to be more K-selected, like birds of prey, owls, eagles, things like that. Some types of plants tend to follow this approach. Elephants humans, we have few babies at a time. There are reasons why people do not have litters. But we take lots of care of them. And so the chances of a baby human surviving to adulthood are way better than a newly fertilized oyster egg, for example. Here's an example, gray squirrels, familiar all around this part of the world. And how old they are, how many individuals were found in this particular study, what proportion of the individuals that we started out with, a set of 530 babies, are still around year to year. And we see nearly 3/4 died in their first year. Okay, and then over half of the ones still alive at that point died in the next year. Being a squirrel is challenging. There are lots of bigger animals, predators that can eat them. There are plenty of potential diseases, parasites, hazards, learning not to run in front of a car, those types of things. And so this looks rather R-selected. A lot of young baby squirrels, a lot of them don't make it. Survivorship. This is the probability that an individual in a particular population, or perhaps a cohort, instead of babies all from the same year, that type of thing, will live to a certain age. And there are various ways of looking at this. We can draw a curve that tells us nicely about the life history pattern in our organism. So, for example, we have something where young ones tend to do pretty well. Most individuals live a while, and then once you get old, and with old age, tend to die more. That's typically the pattern for humans. Another case is where most any time you've got about the same chance of dying. Youngsters, old ones, both seem to have about the same level of risk. Or you have situations where young ones are quite vulnerable. A lot of them die. If you make it past that, then you've got a better chance. And so this is your classic kind of R situation. Something that produces lots and lots and lots of young in the hopes that a few of them make it. Once they do make it past that stage, then they'll tend to live the normal lifespan from there. So here are patterns. What proportion are surviving as young or as old? Again, especially in Western countries where we've got good health care, humans will often survive to adulthood. We have pretty high survival rates to start with, but as we get old, we start to have more problems, and of course, eventually, everybody does die. This straight line was just you got a certain chance of dying, no matter if you're old, young, whatever. Here are the ones where start out and a whole bunch of them die. The survivors then often tend to live for a fairly normal total lifespan. Now, this is generalization. You can have change in pattern in one species during the lifespan, where it starts out following more one, but later follows a somewhat different pattern. A lot of birds. Baby bird, relatively vulnerable, A predator can relatively easily grab an egg or a nestling that can't escape too well. And once they're out of the nest on their own, they have to learn how to manage. Often aren't doing so great there. But once they've got things figured out, if they've survived that long, then they can do pretty well and tend to last out a normal lifespan from there. So, quite close to hatching time, assuming they do even hatch in the first place. A lot of the chicks do die. Maybe the parents weren't able to find enough food, maybe a predator got them, whatever there. But once they've gotten out on their own, learned how to do things, then the survivorship pattern tends to continue relatively stable. So here's a diagram of what that looks like for our, in this case, herring gull. Dying a lot young, and then relatively stable for a long time, and then once they get pretty old, yeah, eventually they're having less success there. This relates to another pattern. Large gulls, like herring gulls, go through a series of 4 different patterns of feathers, the 4th being the adult pattern. So in its first year, once after it's hatched and grown its normal feathers rather than the fluff, it's got a particular feather pattern. Next year, it's got a different pattern, a little bit more like the adult typically. Next year, still another pattern, and then finally reaches the adult in the 4th year. Okay, you go look at a bunch of gulls. What do you see the most of? Well, a bunch of ones dying early. Some keep on dying here. So there's going to be fewer birds that have made it to their 3rd year than are around for the 2nd year. Fewer for the 2nd year, and then were the 1st year. So you do tend to see a lot of 1st year plumages in these gulls that go through 4 plumages. Once you make it past 3 years into your 4th year molt, that's what you keep for the rest of your life. Now they do molt the feathers, but it's the same pattern of what they grow back. So the final adult pattern is in all these ones who are still around past the 4 years. So you see a lot of the adult pattern, fair number of 1st years, and then not so many on the 2nd and 3rd.